All right, so today we'll continue looking at section 6.1. And the first thing we're going to talk about in this section is arc length. Okay, how you can find the length of an arc on a circle. And one fact that's going to allow us to do this, and we just have to trust that this is true, is that arc size and angle size are directly proportional. Okay, so what that means is, as you make the angle bigger in the circle, the arc also gets bigger. Right, so let's say I had a circle, and I draw a 90-degree angle. Okay? There's the size of the arc that corresponds to a 90-degree angle in that particular circle. Right? Now, if I take same size circle, and now instead of a 90-degree angle, I'm going to double the size of my angle. Okay? I'm going to make it 180. Now that's the size of the arc. So since I doubled the size of the angle, what happened to the size of the arc? It doubled. Okay? That's what it means to be directly proportional. If I made this angle half as big, I would make the arc half as big. Right? So size of the angle and size of the arc are directly proportional. Any questions on that? All right, so that's going to allow us to set up a proportion, okay, to find a formula for arc length. Okay? Okay, so I'm going to start with that diagram. Okay, so that diagram has a circle. Okay, in that circle, I have two angles, okay, theta 1, and I have two arcs, S and S1. Any questions on the diagram? Yeah, I've also labeled R, which is the radius, and that's just the distance from the center to the circumference. Now, in order to figure out a formula, okay, we need a starting point. Okay, and I gave you guys an example of this yesterday. If I wanted you guys to come up with a formula, let's say, to convert minutes to hours, okay, you have to already know a conversion in your head. Okay, you have to have a starting point. And the conversion from minutes to hours is that in 1 hour, there are 60 minutes. And as long as I know this, you can tell me any number of hours or minutes, and I can convert from one to the other. You could say, I have 139 minutes. How many hours is that? As long as I have this, I can tell you how many hours 139 minutes is. Okay? Just by solving that proportion and cross-multiplying. If I don't have the starting point to go off of, then I'm stuck. Okay, I can't do anything. All right, so same idea here. Okay, we need a starting point to go off of. And yesterday I said something special. Okay, if this angle is a certain size, then the radius and the arc have certain measurements. Anybody remember what I said yesterday? If you make this angle a certain size, then the radius and the arc, there's a relationship between them. Nick? If you make this angle what? Yeah, how big do we have to make that angle, and it'll make the size of the arc and the size of the radius the same? It is under 90 degrees, but I think we did it in radians. We did it in radians. Denver?
Have a circle with a radius 1 and a unit circle.
Yep, it was right before that. Anybody remember how big you have to make this angle? And if you do that, the radius and the arc come out the same. 1 radian, yes. That's going to be our starting point. Okay, that's going to be our, in 60 minutes, it's 1 hour. That's going to be our starting point. So if the angle was 1 radian, then the arc would be equal to the radius. Okay? So that's my starting fact, just like this could be my starting fact. In 1 hour, there's 60 minutes. Okay? So again, if you make the angle equal to 1 radian, that automatically makes the arc equal to the radius. Right, so now I'm going to set up a proportion. Just like I did with hours and minutes. I just have to do the same thing on each side. Okay, I've got 4 things. 1, 2, 3, 4. I want to set up a proportion. So let's do theta 1 is to S1 as theta is to S. Okay, you can set up your proportion a lot of different ways as long as you put the same quantities in the top and the same in the bottom. So I put angles in the top, arcs in the bottom. Just like here, I put hours in the top, minutes in the bottom. Okay, you just have to keep it consistent on both sides of the proportion. Right, now I want to substitute in what I said. I'm going to change that to 1, and I'm going to change that to r. And that's the left-hand side. Okay, that's your starting fact. And then we're going to use that to figure out anything else they ask us to find. All right, so that's going to turn into 1 over r. Okay, that's like my 60 minutes in 1 hour. Okay, that's the starting point. Equals. And then on this other side is what you would want to know. Now I have to tell you one of the 2 things. Okay? Just like if I wanted you to convert between minutes and hours, I got to give you one of the 2 things. Okay, in this case, I gave you minutes, and I want you to find hours. Right, and that's basically our formula. The only thing they do is they write it without fractions. So does anybody remember the name of the thing you do to solve a proportion?
Cross multiply.
Yeah, you're going to cross multiply. We're going to do that times that equals that times that. So what's s times 1?
1s.
Yeah, just 1s or just s. And then the other diagonal is r times theta. So we get 1s, or you could just say s equals r theta. And that's your formula for arc length. Bless you. Now, some people say, well, how can you assume that it's always going to be 1 radian? Well, it's kind of like, how can you assume there's always 60 minutes in 1 hour? Well, that's a fact. You can assume that. And just because I'm using the fact that in 60 minutes there's 1 hour, I can still convert any number of hours to minutes or vice versa. Okay? This fact doesn't limit what I can do. I can convert anything I want with it. Same thing here. This fact that we started with, it doesn't limit anything we can do. I can use this formula for anything I want. Right? The only thing you have to be careful with the formula is that your angle is in radians. Okay? Because way back at the beginning, I assumed we were working in radians. If I didn't assume that, the formula would be a little messier. Okay? But as long as you're working in radians, it's a very nice formula. S equals r theta. Okay, so S is your arc length, r is your radius, and your angle is in radians. Since these are both lengths, okay, arc length is a length, and radius, that's also a length, they have to be in the same unit. Okay, and they should be in most cases. Okay, but if you ever get a problem where they gave you like an arc length in feet and a radius in inches, you can't do that. You got to have everything in the same measurement. to use that formula. Okay, so I want to use that formula to find the length of an arc. And I have a circle that has a radius of 2 inches. And the angle is pi over 4 radians. Okay, so this is basically what I'm doing. Here's my circle. I've drawn in an angle. The radius is 2 inches, and I want to find the length of that arc between those 2 points. All right, so Ryan, can you remind me what's my formula to find the length of an arc?
This equals our angle in radian.
Yep, and then your angle in radians, and we're just calling it theta. Okay, so Austin, what can I fill in for r here? Yep, radius is 2. And Ian, what about my angle?
Angle would be pi over 4.
Okay, and is that in the right units, or do I have to convert it?
It seems to be in radians.
Yeah, it's already in radians. If it had the little circle above, then I'd know it's in degrees. Okay, so that's already in radians. So we're just going to multiply 2 times pi over 4, which is 2 pi over 4. Right, now, if you can, just reduce whatever you can here. So what does 2 pi over 4 reduce to? Pi over 2. Or 1 pi over 2, same thing. And now, what did I just find? What is pi over 2? It's the what in this problem?
The arc.
The arc. And it's the length of the arc. So if you look back at our problem, how were lengths measured? Like if you took a piece of string and put it on that red line, it would be pi over 2 inches long. Yep. Okay, so remember, lengths are always measured in inches, feet, centimeters, whatever. The angle is always measured in radians. Okay, if they ask you for a decimal, okay, about how many inches is that if you round it, all you have to do is take pi and divide by 2. So it's about 1.57 inches. So any questions on that? Okay, so that's an example where they give you the r and they give you the theta, and you find s. Okay, this one is a little different. They're asking you to find r. Okay, so if they're asking you to find r, they got to give you the other 2 things. Okay, there's 3 things in the formula. You'll always be given 2 out of 3. Okay, so it says find the radius. We've got a circle where the arc length is 3 pi, and the central angle is 60 degrees. Okay, so Hannah, what's my formula again for finding the arc length? Do you remember the name of that symbol?
No.
Anybody help her out?
Theta.
Theta. Yeah. Theta. Theta. All right. Let's start with the 3 pi. What letter does that get plugged in for?
S.
That's S. Okay, that's my arc length. How about the radius? What am I going to plug in for that? Yeah, I don't know the radius. It says find the radius. So that's your variable. And what about my angle? What about theta?
It's been converted.
Right. If I plug it in as 60, it's not going to work because it's not in the right unit. Just looking at it, how do you know it's in the wrong unit? What tells you that? It's in degrees, right? You get the little circle. Right. So how do I convert that to radians? Multiply by what and divide by what?
Pi over 180
Pi over 180.
degrees.
So degrees is gone. And 60 goes into 180 how many times?
3 times. 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 3 times.
It doesn't always go in evenly, okay, but in this case, it does. So we can reduce it. Pi over 3. Okay, so now our goal is to get r by itself. We're multiplying r by a fraction. So does anybody remember the trick to get the pi and the 3 on the other side at the same time? Yeah, times it by the reciprocal. 3 over pi. And 3 over pi. Pi's are gone, and the 3's are gone. And on the other side, what else is gone? Pi's are gone. So what's my radius? 9 feet. Yep. Okay, so that's an example where they give you the s, they give you the theta, and you find the r.
Where did you get that theta over pi from?
That's the reciprocal of pi over 3. So if you have something like a fraction in front of a variable, and you want to move that entire fraction to the other side, you just multiply by the reciprocal. And that'll cancel the entire fraction. And then you just simplify the other side. Okay, any other questions on that one? All right, how about the last type? Does anybody have a question on, let's see, I had you guys find S, I had you find R. Any question on how you'd find theta? Yeah, they'd say you have a circle with an arc length of, 5 units. You have a radius of 6 units. What would theta be? So to find theta, all you have to do is divide each side by r. So you take whatever they give you for arc length, take whatever they give you for the radius, divide them, and that's your angle. And you don't have to label it RAD. Okay? You don't have to label it RAD.
Where does the, say I have like 60 degrees, not 60, say like 43, and then dividing, and it doesn't go evenly into 180, then I get a decimal. Are they exactly reversed?
So if it was like 43 degrees instead of 60, I would just round it off. Since that's not really a nice angle to work with, just type it in on your calculator. 40 times your pi button, divide by 180, and round it off to whatever, I'd say 2 decimal places. Right? And that's the number you would plug in right there.
It's just a number, it's never pi in it.
Yep, radians can be just a number. It doesn't always have to have pi. Yep. It's just like if I said, 17 is just a number, but not every number has to have a 7 in it. Like 23, doesn't have a 7. Yep. So not all radian measures have to have pi in it. Okay. Any other questions on that? Okay, so that's your arc length formula. Okay, so the last thing in this section is what's called angular velocity. What's velocity?
Speed in a given direction.
Yeah, it's the speed of something in a given direction. So angular velocity has to do with measuring the speed of something using an angle. Now, when we use angles, especially when we go around this, I'm moving in what kind of pattern? Yeah, circular. Okay, so when we're measuring speed using an angle, it's usually because something is moving in a circular pattern. Can anybody think of something that you measure the speed of because it moves in a circular pattern? Lots of things if you think about it.
Like orbits of planets.
Okay, yeah, orbits. Our year is measured as it's a 365 days in 1 year because it's orbiting, the sun. Yeah.
Wheel speed?
Yeah, wheels. You measure the speed of a wheel possibly spinning. A lot of times you don't use angles, but you use revolutions per second. It's the same thing, or revolutions per minute, RPMs. So if you have a tachometer on your car that measures the engine speed, that's measuring the speed of something spinning. How many revolutions is it doing per minute, per second, per hour, but whatever the time unit is. So our book defaults to using radians. Okay, so if they ask you to find the angular velocity of something, normally that would be a pretty wide open question. Well, what do you want? Do you want degrees per second, degrees per hour, radians per minute, revolutions per minute? But the default is if they ask you to find angular velocity, you always use radians. Okay? I don't care what time unit you use. Use whatever's in the problem. So if they give you information in seconds, you could find a speed in radians per second. If they give you information in hours, you could find a speed in radians per hour. All right, but radians is kind of the default unit unless they say to do something different. Right. So I want to take a look at why do you even need angular speed or angular velocity? Why don't we just do everything like we normally do? Why don't you just always use like miles per hour or feet per second? Because we already have a way to measure speed. So why don't we just use that? Any thoughts on why we don't use that? Something spinning on a circle or something moving, in a circular path, it's a little different when you try to measure the speed of it. Right? Let's take a look at this picture. So what I have here is 3 dots. Okay, one kind of as close to the center as I could put it. The red dot a little further out, and then another black dot closer to the edge of the circle. Now, if I go like this, how many revolutions did all 3 dots just make? They all made the same number of revolutions. Right? Everybody agree they all went around one time? Except the one in the center kind of stayed as close to the center as it could. But as they moved around, which dot is moving the farthest? Which one's traveling the greatest path?
The further over.
Yeah, the dot that's further out from the center. Okay? So we all agree that the one that's closest to the edge is traveling the furthest. But they're all making the same, they're all doing that in the same time. Right? Each one of those dots made 1 revolution in exactly the same time. However long it took me to go like that. Well, let's look at our regular distance formula. If an object is traveling more distance and it's doing it in the same time, what does that mean?
It means it must be going faster.
It must be going faster than everything else, right? If you and your friend both leave at the same time and one of you ends up farther than the other one, well, the only way that can happen is if, assuming there were no delays or anything like that, one of you was traveling faster. All right? So that's the problem here. If you try to measure this using linear speed, all 3 of those dots are traveling at different speeds. The one in the center is traveling at 0. It's not moving. Okay? The red one is moving a little faster, and the black one is moving even faster on the outside edge because it's covering more distance in the same time. So it must be going faster. But it's kind of confusing to think of things that way. So that's why we use angular speed. And that way I can say all 3 of these dots have the same angular speed. 1 revolution in, maybe that took me 2 seconds. Okay? So they all have the same angular speed. Yeah.
Are you ever going to have us, like maybe in a question, find the speed of the individual dots, or?
Yes, but what that would basically be like is, let's say I had a tire spinning at 200 revolutions per minute, and I dropped the tire on the ground all of a sudden. How fast would the tire go if it just took off straight?
Yeah.
That's basically what that would be. Yep. Or another example would be like, let's say you have an object and you're swinging it, like like a lasso or something, or a rock on the end of a rope. Yeah. So you're swinging the rope, right? Maybe you're swinging it at 60 revolutions per minute, so it's going around like once per second, and you just let it go. How fast would it go in a straight line? Okay. That would be an example of what you just said. Okay, so angular speed, as I said, the default is to always measure it in radians. per time unit. Probably not what you're used to. You're probably used to like revolutions per minute, or revolutions per time unit. Okay, but we are going to practice a little with radians. And just to compare that to linear speed, that's the speed of an object moving in a straight line. Okay, and that we measure in miles per hour, feet per second, kilometers per hour if you're anywhere but the US.
So angular speed and velocity is the same thing?
Angular speed, angular velocity is the same thing.
Okay.
Yep. Angular speed or angular velocity. Same thing. Okay, and there's all kinds of formulas you can learn to try to convert between the two, but it starts to get confusing when you start learning all these formulas. So the way we're going to do it is by canceling units, okay, dimensional analysis. Okay, it's exactly the same way I was teaching you how to remember the conversion between degrees and radians. If you want to cancel a unit, you have to put it in the opposite spot in the fraction, and it cancels. Okay? That's a lot easier to remember than tons of fancy formulas. Now, you do need to know basic conversions. Okay? You have to know things like how many seconds in a minute, how many minutes in an hour, days in a year, hours in a day, inches in a foot. Okay, you have to know those things. All right, so let's take a look. Okay, the first one we're going to do, it's simpler than a speed. Okay, speed is a rate. It has two parts to it. It has a distance part and it has a time part, like miles and hours, miles per hour. This is just a single thing, days. I just want to try changing days to minutes.
We did stuff like this in physics.
You've done some conversions?
Yeah.
Okay. So I have 3 days. If I want to convert that to minutes, I'm going to go one step at a time to smaller units. So you start at days.
Hours.
What's the next time unit down from a day?
Hours.
Hours. So now I need a conversion. How many hours in a day?
24 hours in 1 day.
24 hours in 1 day. So now I have two choices. It's either 24 over 1 or 1 over 24.
24 over 1.
Right. Okay, I want days to cancel. So I'm going to put days in the bottom. I'm going to put hours in the top. If I put days in the top, it wouldn't cancel because days is in the top on the other one. So 1 day, I wrote days, whatever. In 1 day,
1 days.
24 hours. Yeah, it's a days. All right, now I want to go down the next time unit from an hour. Is what?
A new minute.
A minute. So now I need a conversion between hours and minutes. 60 minutes in an hour. Do I want hours in the top or in the bottom? I want it in the bottom because, again, I want it to cancel. So 1 hour, 60 minutes, and that's the unit I want. So let's look at what cancels. Hours in the top, hours in the bottom, days in the bottom, days in the top. What's the only unit that's left in the whole problem? Minutes. Now just multiply out everything in the top and divide by the product of everything in the bottom. In this case, the bottom is just 1 times 1. Okay, so we don't have to worry about that. So we have 3 times 24 times 60. Gives me 4,320 minutes, okay, in 3 days. All right, the next one we're going to do, this is a rate. Okay, so this has 2 components to it. It's got a distance and a time. Okay, so it tells me that I'm traveling 50 feet per second. Well, that's 50 feet in how many seconds? 1. 50 feet every 1 second. So 50 feet every 1 second. So now you kind of tackle each part of this separate. You have to change feet to miles, and you have to change seconds to hours. Okay, which one do you want to start with? Do you want to start with the distance or the time? Distance. All right. So we're going to try to get rid of feet and get it to miles. So where does feet have to go to cancel out? Bottom. Miles has to go in the top. Now I need to know how many feet in a mile.
5,280.
Yep, 5,280 feet in 1 mile. That's the conversion. If I stopped at this point, I would now have units in miles per second. Okay, but I want miles per hour. All right, so now we have to get seconds to hours. So what's the next unit up from a second?
Minutes.
A minute. So I'm going to put minutes in the bottom, seconds in the top. And we just did this. There's 60 seconds in 1 minute. Seconds in the top, seconds in the bottom. Now, if I stopped here, I'd have a speed in miles per minute. Okay, I want to go one more step and change minutes to hours. So where would minutes go?
Top.
Yep, minutes in the top, hours in the bottom. And we just did this one as well. 60 minutes, 1 hour. Okay, so now for a distance in the top, you're left with miles. There's nothing else. In the bottom, you're left with hours. Some people write it as MPH, miles per hour, or you can just write miles / miles per hour. Right, so let's see what we got. So multiply everything in the top. 50 times 60 times 60. And divide by 1 times 5,280
Divided by 5,280.
times, yeah. Okay, so it's about 34.1 miles per hour.
Is there like a specific unit you should do first, like whether it's distance or time? That
Nope.
makes it, no?
Nope, it doesn't matter. It's just going to change the order of these
Yeah.
fractions. But you're still going to multiply everything in the top and divide by the product of everything in the bottom. All right, so the last one we'll do, and then we'll start looking at unit circle trig, but we're not going to finish it until tomorrow. I want to convert one that's an angular velocity, 200 radians per second. So we have an object that's spinning at 200 radians every second. And I want to convert that to revolutions per minute. Let's deal with the time unit first, because that's just one step. So I want to convert seconds to minutes, and it's only one time unit I have to go through, just seconds to minutes. Okay, how many seconds in 1 minute? 60. So now my speed is radians per minute, okay? But I want to get that to revolutions. All right, so now I need a conversion between radians and revolutions. Even if I don't know it, where is radians going to go?
Bottom.
It's going to go in the bottom, and revolutions in the top. Now I need to know the conversion. So 1 revolution is 360 degrees, but I'm not doing degrees here. How many radians in 1 revolution? 2 pi, yes. 2 pi radians in 1 revolution. Okay, and now you just multiply that out. 200 times 60 divided by 2 pi. Does anybody need me to type that in? You just type it in and your speed would be in revolutions per minute, which some people write as RPM, revolutions per minute. But you just type it in. Okay, and the last one is going to be one like James said about converting an angular speed to a linear speed. Okay, so that's like a tire spinning on like a balancing machine. You drop it on the ground, it doesn't lose any traction, and it takes off straight. How fast would it be going? All right, so we have a wheel that has an 18-inch radius, and it's spinning at 1850 RPMs. That's revolutions per minute. Okay, anytime you see RPM, that's what RPM stands for, revolutions per minute. Okay, I want to find the angular speed in radians per second. You know what? I think I'm going to skip that because we just did part A in the last problem. Convert between radians per second and revolutions per minute. That's exactly what we just did. So I'm not going to do part A because part A doesn't help us to do part B anyway. So let's just find the linear speed of a point on the wheel's circumference. So what's the angular speed of this wheel? How fast is it spinning?
1850 RPM.
And that's 1850 what?
Revolutions per minute.
1,850 revolutions every 1 minute. So that many revolutions in a minute. All right, I can see in my final answer they want seconds. Okay, so nothing new there. We're going to change minutes to seconds. Okay, so in 1 minute, 60 seconds. Okay, so we've taken care of the time unit. Now we have to get revolution to feet. Okay. So where is revolutions going to go? Top or bottom? Bottom. Feet is in the top. Now, how do you figure out how many feet in a revolution? What is that really? If you're trying to find out how many feet in a revolution. Okay, like imagine you mark a tire, right? And you put it on the ground, and then you roll the tire on the ground one time until that mark comes back on the ground again. And then you look at the distance the tire moved. What is that? Denver? It's the circumference of the tire, right? If you put a chalk mark on a tire, put it on the ground, and then roll the tire one time until the chalk mark comes back on the ground again, and look at the distance the tire rolled, that's the circumference of the tire. Okay? So to figure out how many feet in one revolution of the tire, you need to know the circumference of the tire. So circumference is 2 pi. What's the radius of the tire? 18. So the circumference is 2 times 18 is 36 pi inches. Okay, so if you took this tire and you let it roll on the ground one revolution, that's how far it would roll away from you. We don't have to figure out what that is. Okay, that's 36 pi inches in one revolution of the tire. Now, what's different about this conversion is it changes in every problem. There's always 60 seconds in a minute. There's always 24 hours in a day. There's always 12 months in a year, things like that. Those conversions never change. This conversion changes depending on the size of the tire. There's not always 36 pi, I need to fix that. Yeah, there's not always 36 pi inches in a revolution. It depends on the size of the tire.
So you'll always be given enough information to find that though, right?
Yes, you'll always be given the radius and you'll have to find that. So the mistake I made is I put feet. It's measured in inches. And then if they want it in feet, how do you change inches to feet?
60. 1 times 12.
Yeah, in 1 foot, there's 12 inches. Okay, and what else cancels? Revolutions. And now I'm left with feet in the top, seconds in the bottom. So this would tell you if this tire was spinning on a machine and you just drop it on the ground and it took off, it would be going that fast. We just have to type that in. It's on your calculator. You do 1850 times 36 times pi. And then you divide by 60 times 12. Did anybody type that in?
720.
720 feet. Did anybody else get that?
Yeah, that makes sense, because 6 times 12 is 72.
That's pretty fast, because we know,
Well, that's what I just got the product of the denominator.
Yeah, don't you still have to divide
Yeah.
by the bottom?
yeah, because that would be several hundred miles per hour.
Oh, wait.
So did anybody do the whole thing out?
Oops.
Yeah, so the product of the denominator, 60 times 12 is
Wait,
720.
So would you do 1850 times 36 pi?
Yep, 1850 times 36 times pi, and then divide by 720.
It's 290.6.
290.6. Okay, so that's pretty fast. I mean, 290 feet per second, that's about 6 times faster than 50 feet per second. So 34 times 6, it's over a couple hundred miles an hour. But
Wait, can you go down to what that answer is? 290.
okay, so any questions on that? So again, you can learn all kinds of fancy formulas, but without memorizing, this is the easiest way. Just look at where you want your units to cancel and know basic conversion factors. All right, so the last thing we'll take a look at, but we're not going to get into too much, is unit circle trig. And I'm not going to write out, I mean, I have it all written out, but I'm just going to say what the idea is for unit circle trig. I think if you look at the diagram, it'll make sense. Okay. You can give me any angle you want, okay, and I can sketch it on this circle. Okay, this angle looks like it's about 140 degrees or so,
What's this section called?
from here to here.
Unit circle. Okay.
And when I sketch an angle, it's got an initial side, and it has a terminal side. Well, as I draw the terminal side, it's going to come out, and it's going to hit the edge of the circle somewhere. Okay? Every single angle has a terminal side that's going to hit the edge of the circle. And my goal with unit circle trig is to find the coordinates of where the terminal side hits the circle. That's the whole idea. Okay, so here's another example. No matter where I draw an angle, let's draw a 45-degree angle. There's a coordinate for where that terminal side hits the angle. Okay? I want to know, what's that coordinate? If I can figure out the coordinate, then I can do trigonometry on a circle. So any questions on the idea? Trying to find a coordinate for where the terminal side hits the edge of the circle. Now, you can only do this for certain angles. The only angles we're going to do it with are ones that are multiples of 30 and 45. Okay, we don't do unit circle trig with angles like 16.4. Okay, we only do it with nice angles. Okay, and as long as you know the x value and the y value for that coordinate right there, we can define our 6 trig functions using that coordinate. But you have to know the x and you have to know the y. All right, so this is the first time we've seen the trig functions in this class. Okay, so the 3 basic ones are sine, cosine, and tangent. And I wrote their abbreviations underneath. Okay, if you want to find the sine of this angle right there, as long as you know the coordinate, all you really need for the sine is the y value. Okay, so if you know the y value of this coordinate, that would be the sine of this angle. Okay, that's a definition. If you wanted something called the cosine of that angle, well, you draw it, find the coordinates of that point right there, and for cosine, all you need is the x value. If you want the tangent. Okay, it's something else we'll use in trig. If you want what's called the tangent of that angle, you need both the x and the y value, and you divide them. Y divided by x. Okay, so to find those three, you have to get this coordinate first. If you can't figure out the coordinate, then you're not going to know any of the x's and y's, and you can't find anything I just showed you. Right, and there's also three other trig functions. There's cosecant, secant, and cotangent. And I put their abbreviations underneath. Usually an abbreviation just uses the first three letters of the function, but you can't do that with cosecant because you've already used those three letters somewhere else. So they just go by syllables for that one, cosecant. Now, these three are easy to remember if you know the three on the left. These are all the reciprocals. So think of y as y over 1. What's the reciprocal of that? 1 over y. And secant is the reciprocal of cosine. So what would that one be? 1 over x. And cotangent is the reciprocal of tangent. X over y. So as long as you can remember the three on the left, the three on the right are just flipped. Okay, they're the reciprocals. Okay, there's 4 special angles that pop up sometimes. And we call them special angles because they land right on the axes. They're not in a quadrant. They're on the axes, which separate the 4 quadrants. And those 4 angles are your 0, 0, 90, 180, and 270. Now, these 4 points all have something in common. When you find the coordinates of any one of these points,
They'll always have a 0.
they're always going to have a 0 for one of the values. Yep. Either the x value or the y value. Not both, obviously, not both. But one of them will always be a 0. Okay, so these are called the quadrantal angles. And then the last thing, and then we'll just try some examples with the time we have left. Okay, so how do you actually do unit circle trig? Like if I gave you the point 0, 1 and said, find all 6 trig functions that correspond to this point, 0, 1. Well, step 1 is to find the point. You might be like, well, wait a minute, you just gave us the point. Yeah, yes, I did in that one. Okay. You are going to have some where you have to find the point yourself. But if they don't give you the point, you have to find it. Okay, so in example 1a, step 1's already done for you. Step 2 is to take the x value, take the y value, and just plug those 2 numbers in those 6 formulas. Now, on the test, I wouldn't have a question where I ask you for all 6 in the same problem. I'll do all 6 now, but on the test, I would only ask for 1 out of the 6 we're about to do. Okay, so this point represents an angle. You might even know the angle. If you graph the point, I think you could probably figure out. You haven't gone left and right, you've gone up 1. Here's your initial side in standard position. There's your terminal side. The terminal side goes right through the point 0, 1. So you probably could figure out what this angle is. I don't care what it is. All I care about is what is the sine of the angle, the cosine of the angle, and the tangent of the angle. So the goal is not actually to figure out what is the angle. It's to find out the sine of the angle, and so on. Okay, so using this coordinate, what's the definition for sine? What letter is it equal to? Sine is equal to y. So the sine of this angle, whatever it is, pretend we don't know, the sine is 1. Okay? How about the cosine? What's the definition for cosine?
X.
It's the x. What's the x in this case?
0.
0. So whatever that angle is, I don't know what it is, it has a cosine of 0. And what about tangent? How do you find tangent?
Tangent's 0, right? Because it's y over x.
It's y divided by x. So what's 1 divided by 0?
Yeah, it's like nothing. That's not even.
So what do you think you would write?
No error.
Error, we usually write
No
undefined.
solution. Undefined. The calculator would say error.
You can't divide by 0. Okay? Now, once you get the 3 on the left, what did I say you do with each one of them to get the 3 on the right? Yeah, just flip them.
Oh, wow.
So if you have the number 1, you might be like, well, wait, how do I flip 1? It's not a fraction. Well, you can make it a fraction. It stays 1. Now, the secant, be careful with this one. It's 0. How do you make 0 a fraction? Same way you make any number a fraction. Put it over 1. So what do you get if you flip 0 over 1?
Undefined.
That's undefined. And your cotangent?
Stays.
Well, this was undefined, right? It was 0 over 1. So when you flip it, now you have, when you flip it, now you end up with this.
0 over 1. So that's 0.
That's 0. So the point, when you flip 0, you get undefined. When you flip undefined, you get 0. That's the only special case. You just got to be careful when you divide by 0. All right. Let's try this one. Now, this is one I guarantee you don't know the angle for because there's no 0 in the coordinate. So it's not a quadrantal angle. What's the sine value?
Square root of 3 over 2.
Yep, and we just leave it like that. That's it. What about the cosine? 1/2. And what about the tangent?
Square root of 3 over 2
That's y
divided by 1/2.
divided by 1/2. Now, when you're dividing fractions that have the same denominators, what can you do with the 2's? Luke?
Oh, gosh.
Yeah, some people like to flip and multiply by the reciprocal. It's the same thing. But the 2's cancel. And you get just square root of 3.
Would you want us to simplify that?
No, that's as simplified as you need to get.
No, I mean, okay, so square root of 3 is simple.
Those are final answers. Yep. And then if I wanted the other 3, I would flip them. So like the secant would be 2 over 1. The cotangent would be 1 divided by root 3. Things like that. Right, so I just flip them. Okay, so I'm only going to find the 3 basic ones. And these are all the same. Let's do this one. What's different about this example? It's not a point. Okay, you can't do anything until you figure out the point. So if you're not sure where 90 degrees is, draw it. And remember, we're doing unit circle trig. So we're drawing everything on a unit circle. Where's 90 degrees?
Is that just, yeah, that, straight up.
Straight up. So what would be the coordinates if you go straight up
0, and then whatever.
and it's a unit circle?
Oh, 1?
1.
Oh, we just did that.
So now your x is 0, your y is 1.
Yes.
Just plug them into those formulas. And we literally, I think we just did
Yeah,
one.
we just did 0.
We just did that problem. Okay. What about 270? Where is that?
Down.
Down. So what's the coordinate?
0, -1.
Yes. And now that would be very, very similar to the last one, except just be careful. Now you're plugging in a -1 for y and a 0 for x.
No.
How about pi? Anybody remember first what that is in degrees?
180,
Yep. And now if you draw 180, where's 180?
that's left,
Left? And what's the coordinate there?
so y is 0.
Yep,
So -1.
negative 1, 0. And you're going to get the same kinds of answers,
Would
okay?
there ever be a question like find the 6 trig functions of like 84 degrees?
Nope. I might ask you to do one of 30, but not today.
Okay,
We'll talk about that tomorrow.
all right.
Okay? So you just have to find your coordinate and then fill in your numbers. All right, so the homework on 324, okay, I want you to try 56 to 59, 70, and 71. So just 5 questions on that page. Sorry, 6. And on page 335, there's only 3 questions from the book. Okay, I want you to do 1, 5, and 8. Follow the directions they ask you to in the book. And I want you to do something else with those questions. I want you to do what we just did in the last 3 examples. Find the 6 trig functions of 1, 5, and 8. Okay? And try finding the 6 trig functions of 3 pi over 2, 2 pi, and this coordinate. Okay, so I'm looking for the sine, the cosine, the tangent, the secant, the cosecant, and the cotangent of this, that, and that. Okay, and we'll take a look at that tomorrow.